Hello, how you doing? In this video, I'm going to talk about Pinecone fetches and queries. Have you seen how easy it is to use Pinecone's native client library to perform Pinecone vector database fetches and queries? Well, if not, then watch along with me for the next few minutes and I'll quickly show you. Okay, let's get started. Before we get into fetches and queries in Pinecone, first, you need to get a Pinecone account, and second, you need to get an API key. In an earlier Pinecone video on Pinecone indexes, I cover what you need to do in both of these steps. If you want to see this in more detail, feel free to go back and watch this video. But for now, we'll keep moving along. In this video, I'm going to show you examples in Python, but you can integrate to Pinecone natively with a variety of languages. Pinecone has SDKs for Python, Node.js, Java, .NET, Go, and Rust. In any language you use, you'll first need to download the respective Pinecone client library. In Python, you can do this using pip install to download the Python library. The Python code I show you can be executed using Jupyter Notebooks or any Python code IDE such as Visual Studio Code. The first thing you'll need to do if you follow along with this Python code is import time and then import the Pinecone and serverless spec classes. This brings in all your dependencies into the Python runtime. Next, you instantiate a Pinecone object and you pass it your API key. The Pinecone object will use this API key on REST API calls to the Pinecone backend in the cloud. Now let's create the index we'll use to fetch and query vectors. To do this, call pinecone.createIndex, where you provide a number of parameters. In an earlier video on Pinecone indexes, I stepped through each of these parameters in detail. First, I pass the index name. Next, I pass in the dimension parameter. Normally, the dimension will be much larger, but for this example, I set the dimension to 3 so I can demonstrate visually the vectors in the Pinecone database after the upsert, fetch, and query operations. I keep the metric parameter set to cosine. The metric parameter defines which similarity search algorithm Pinecone will use when performing query operations. The default metric value is cosine, but you can also use Euclidean or dot product. If you're unfamiliar with the basic mathematics behind these similarity searches, I have a video covering similarity search metrics where I break it all down for you. I'll share a link at the very end of the video in case you're interested. Note, the index creation is wrapped inside an if block that checks if the index is already created, and if it is, we skip, move on, otherwise we create the index. After the index is created, we get a Python object reference to the Pinecone index. We use this Python object reference when we perform CRUD operations on the index. Using this Python index object reference, we can upsert vectors into the Pinecone index. Here I upsert 4 vectors with IDs of A, B, C, and D. After this, I read them back using a fetch operation. You can fetch up to 1,000 vectors at a time. Pinecone is eventually consistent, so there can be a slight delay before new or changed records are visible to queries. When I make my fetch call, I pass in the IDs for my 4 vectors. The fetch call returns results back and then prints them out to the console. Here are the results printed out to the console after running my Python script containing my upsert operation. You can see the vectors A, B, C, and D are all in the Pinecone index. When you use the fetch operation, you're simply performing reads on the vectors you specify in the call. So if you imagine these vectors in 3D space, you can see visually that we now have 4 vectors in the Pinecone index. So how do we query vectors from a Pinecone index? Well, it turns out this is also pretty easy. Here's a Python script that performs a query operation. The first parameter is the query vector that you're searching for similar vectors to. This should be the same dimensionality as the vectors in your index. The second parameter is top k, which is the number of the most similar vectors you want to retrieve. For example, if top k is equal to 3, it will return the 3 most similar vectors to the passed-in query vector. The third parameter is include values, which is a Boolean flag indicating whether the actual vector values should be included in the results. If it's set to false, only the IDs and metadata of the nearest vectors are returned. Otherwise, everything, including the values, are returned. In upcoming videos, I'll cover Pinecone vector metadata, but for now, we'll keep moving along. Now, if you remember when we created the Pinecone index, we specified cosine as a metric parameter. So how does this impact query operations? Well, the selection of the metric determines which similarity search algorithm Pinecone will use when performing query operations. In our case, with cosine being the metric, the Pinecone query operation will use the cosine similarity algorithm. Cosine similarity measures the cosine of the angle between two vectors. It ranges from -1 to 1, where 1 indicates the vectors are identical, 0 means they are orthogonal or have no similarity, and -1 indicates they are diametrically opposed. The metric is particularly useful for understanding the orientation of the vectors relative to each other regardless of their magnitude or length. Here is the console output after running my Python script containing my query operation. Note the top k value is set to 1, so we only get back one vector. For right now, you can ignore namespace, as I'll cover this in an upcoming video. So quickly, if you imagine these vectors in 3D space, you can see the 4 vectors in the Pinecone index, plus our past-in query vector. The query vector is notated as Q in the diagram. The vector with ID equal to D is closest to the query vector Q when measured using the cosine metric. So this is why the vector D was returned in the query response. Quick reminder, Pinecone is eventually consistent, so there can be slight delay before new or changed vectors are visible to queries. You might see this if you do a vector upsert on an index and then immediately try to do a query on that same index. So what is the difference between fetches and queries? Fetch operations retrieve vectors by their IDs, while query operations search for vectors similar to the query vector passed in. Understanding when to use each is important for optimizing your application. If you're looking for a vector and you have the ID, you should use the fetch. Fetch is the most efficient option. It directly retrieves vectors without performing any similarity search. You should use a query when you need to perform similarity searches to find the most relevant results based on the query vector. Query is more computationally intensive than fetch, but it's essential for tasks that require ranking and relevance. Okay, so now you should have a basic understanding of both Pinecone fetches and query operations. In upcoming videos, I'll be covering namespaces and metadata. Feel free to check these videos out to see how easy it is to take advantage of these Pinecone features and use them in your LLM-driven systems. Okay, thanks for watching. This video, along with all my other videos in the Vector Databases playlist, are listed in the YouTube description. I invite you to watch other videos on my channel. If you like the way I'm sharing this content, please consider subscribing. When you subscribe, this really helps my channel grow. One last thing, we all love technology and we're all excited about all the innovation with the cloud, machine learning, AI, but don't forget to carve out some time to live in the real world. Go outside, go swimming, go hiking, go climbing, go surfing, but get out and move your body. And if you do, tell me in the comments. I want to hear about it. And with that, have a great day. Thanks.